Uh, all right, so probably I should reinstall this device because I can't write here. Okay, so you have back to the slide. You have two components, fx and fy, and the important thing is here is that how you derive these two components. So first you have to draw your frame of reference. So if you have a vector f, then you have to draw x and y directions on the space, as you can see on the left side, and so you would get an angle between the vector and the two directions. So here theta is the angle between f and the x component, and so you multiply the magnitude of your vector by cosine of theta and sine of theta to get the x and y components. Well, this magnitude could be defined as the square root of fx squared and fy squared. So, well, okay, so I'll get back to your question, Sammy, on the resultant vector. But is there anyone having any questions about these components of vectors or the sine or cosine? No questions. So everybody know how to. Okay, so about this resultant force, so I'm going to get back to the previous slide. So replace F with R for the resultant vector formula. Yes, well, in this slide, well, if you compare these two slides, yeah, here F is the resultant of Fy and Fx. So that's it. And so let's go to an example. Well, we would clarify more this vector decomposition. So in this example, we have three vectors. You already have the reference frame XY. It's a two-dimensional problem. So if you don't have any Cartesian axis, then you have to draw it in the space. This is very important. And if you have it, then you immediately go to the vector decomposition. So I'm going to let you some time to solve this problem. So here you're asked to calculate X and Y component of the forces. We have three forces, and you don't have the angles here, but you have the dimensions in X and Y, so you must be able to calculate sine of theta and cosine of theta. So if you have any problem with that, please just give me a text so I can unmute you to ask questions. Okay. Let me see how. All right.
Hey, Siavash. Merci. So for this problem, I see that the
Let me
actual
see.
force vector has a certain length, and then the dashed lines continue past that. When I took the class last, the force vector would continue all the way, but because the dimensions are given, I simply use the dimensions to find theta.
Okay. Can you ask your questions again?
Yeah, of course. No problem. So for this problem, the
Mhm.
dimensions, I use the dimensions to find theta. And then once I find theta, f cosine theta would be the f sub x, and f sine theta would simply be f sub y. And that's how we find the components for this problem?
Yes, exactly.
Okay.
So
Thank
you have the dimensions. So you calculate sine of theta and cosine of theta as the coefficients for the magnitude of f. And if you multiply them, you get fx and fy.
you.
So you have, for example, for 800, you have 600 in the y direction, 800 in, for the 800 Newton force, the force on the top right, you have 600 in the y and 800 in the x direction. So
So it's simply trigonometry, just tangent theta equals what, 600 over 800.
yes. So okay. So you could derive theta and then calculate. So if you get the tangent and use your calculator to derive the angle based on 600 over 800,
Right.
which is actually that is not my favorite solution. So usually people uh, directly calculate sine of theta and cosine of theta. So what is the definition of sine of theta? It is
Opposite. No, sorry. Yeah, opposite over hypotenuse.
okay. So first you derive the hypothesis.
Oh, that it's 100. I mean, sorry, 1,000.
Yes, and
Oh, okay. I think
the
okay.
hypothesis here is 600 plus 600 squared plus 800 squared. That would be 1,000, and so
Oh, and then you just do 800 times 600 over 1,000, and then 800 times 800 over 1,000 for f. So you'd like us to substitute the actual relationship from the triangle from
yeah,
our 700. Okay, I understand.
yeah.
Gotcha.
So this way, you're not using your calculator to 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 actually calculate some arc tangents, and that is also actually a source of error. So that's why people directly use the definition of sine and cosine.
Because it's not fully accurate.
And well, it is also more fundamental because you derive tangent from sine and cosine. So when you have sine, when you have the dimensions, you can directly calculate them.
Gotcha. Thank you so much, Sevash.
No problem. And any other questions?
That's all from me. I'm going to mute myself. Thank you so much.
Sure. Let me. Okay. So let's go to the solution. So for the 800, as I said, you calculate sine of theta and cosine of theta based on the division of x and y coordinates. So for f of x, for the 800, the you must multiply 800, which is the magnitude of this vector, by the cosine of theta, which is 800 over hypotenuse, and that's 800 over 1000. So this way you get fx. That is a positive number because f of x lies on the positive x-axis. This is also important to always know the sign of the forces you're calculating. Because when you're using sine and cosine, you do not directly get the sign of the scalar for the components you want to calculate, but but if you refer to the diagram, you can easily see whether it is positive or negative. Anyway, my words might not make sense that much at this point because we are simply calculating some forces, but later in the course, when you have multiple forces in the system and you have some values of theta, you definitely need to pay attention to the signs. So for Fy, then you have the adjacent, so the opposite side over the hypotenuse, which is the definition of sine of theta. So it is 600 over 1000. So it would give you 480 for the Fy. And well, you can check if this is the correct answer by using this middle formula for the magnitude of f, this square root. So if you take fx squared plus fy squared and take the square root, you must get 800. So this is also a way to check your answers. Is there anyone who has problem with calculating this 1000 in the denominator? So everyone's clear about 1000. Okay, 1000 is actually the hypotenuse. It's the hypotenuse of the triangle. So this is the way that we get sine of theta and cosine of theta. So I repeat, sine of theta is the division of the opposite side over the hypotenuse, and cosine is the division of the adjacent side over the hypotenuse. Okay, so for the next force, we have actually similarly calculated this one. So here, the x component is actually the adjacent side, so you must take the cosine. So it is 560 over the hypotenuse length, and it has a negative sign, and Fy lies on the y direction. So if the angle, so I'm really sorry that I don't have my pen here to show you the angles, but if you can see my mouse here, it's between 424 and x. So I'm taking sine of this theta between any vector here and the x direction. So this way, sine of theta would give you f of y. Okay, in response to Carlos, yes, this is the method that we use in all statics problem. Well, there are exceptions, but just this is the most fundamental and mathematically sound way of calculating the components. So there's no alternatives. Any other way would be derived from this method that we are already practicing. Okay, so we have another force. So this one, you can see I repeat, the theta is here is the angle between the vector and the x components. So cosine of theta times the vector would give you x component, and sine would give you the y component. So this time fx has positive sign because the projection of this vector on the x-axis would lie on the positive x-axis, and the y component on the negative y. That's why we have a negative y, a negative sign for the y component. Okay, any questions? Any more questions here? Okay, so Dor or Dorev, it is not incorrect to use arctangent, but I highly suggest that you don't do that, because you're going to use your calculator when it is not actually necessary. So when you have the dimensions, you could use the definitions of sine and cosine, trigonometric definitions to calculate these two functions. But you can also, well, you always have your calculator even in your exam. You can calculate the arctangent and then sine and cosine by the calculator. That is also possible, but so I suggest that you always you use that method. Okay, apparently we have limited time here. Yes, you can move the vector on its line of action all the time. There's no exception, unless you want to calculate the moments of the vectors. You'll get to that point later, but for now, you can always move the vectors. Mathematically, it is correct. You can unless it is asked in the question to derive the forces in a certain unit, it's okay. You should do that, but you know you don't need to you don't need to convert that. But it's always good to know to have the conversion units with you. Well, it's a bit different in the United States because they use American units, pounds, and foot, and because it's not like this in other places around the world. Like in my country, Iran, we use SI units, so we always use Newton. That is more actually used in Europe and other places, but pounds are pretty much usual in the United States. Okay, so all right. I hope my responses were helpful. So let's go to another problem. This is a bit more challenging. We have a hydraulic cylinder BD that is connected to a rod ABC, and it is exerting a force on at point B, and you know the components perpendicular to ABC, which is 750 Newton. And so when you know this component, it's just a hint. It's better to draw your reference frame with respect to that component. So if you have a component perpendicular to member ABC, so you must have a reference frame that lies, one of its direction lies on this component and the other perpendicular to that, which is along ABC. So then you are asked to calculate the magnitude and its components parallel to ABC. So everything is similar to the previous problem, except that you have to draw the frame of reference here. So, well, I have shortage of time today, so I'm going to, because we have another problem to deal with, and that's going to take more time. So I'm going to go to the solution. So just to remind you, all the questions here are related to your first homework. So for your second homework, we will discuss everything about that in the next session. So this session is just about the vector decomposition and some points about cable forces or tension forces. So in this problem, so you should draw the frame of reference, which we don't have here. So then you have to decompose the force. So the frame of reference here is along ABC and perpendicular to that. We know from the problem that we have 750 Newton components perpendicular to ABC. So what is the perpendicular component to ABC if we consider the angle between ABC and BD? So the perpendicular component would be magnitude times the sine of this angle here between BC and BD. So how do we derive this angle? So it's a trigonometry problem. It's a geometry problem. So you can simply derive the other two angles of triangle CBD and then subtract them from 180 to get this angle. So again, because I'm not showing this here, unfortunately, this angle I'm talking about is CBD. So that would be 20, and we know the perpendicular component is the force times the sine of that angle. So P sine of 20 would be 750, and then you can derive P. Any problems here? Any questions here? Let me. I'll try to see what's the problem with this device. Last time I checked it, it was working, but I don't know what's. Maybe I can use my mouse. Okay, so this is the angle I'm talking about, and this is your so let's say this is X and this is Y, and this is the direction of your force. Okay, so this theta, so this angle here is 90 minus 50, which is 40. And this angle here is 180 minus 60, so this is 120. So theta would be 180. All right, let me see. So theta is actually 180 minus 40 minus 120. Okay. So any questions here? So then we know the component in the y direction, and which is 750, and by definition it is the magnitude of the force times the sine of theta, and so that would give you the magnitude of the force. And using the same method, you can calculate the components. Okay, this Q actually does not have any magnitude or any definition here. So it's just showing that you're exerting a force on point A, because otherwise you don't get any internal force in the BD elements. So you must have some force at point A to get some force at point B. Think of it physically. Otherwise, there would be no force in the system. But it doesn't matter what's the magnitude of Q, because you know the components. You know the components. This is 750, and P actually is the force. If you see the first line, is the force that BD exerts on member ABC, and it does not have anything to do with Q. Any more questions? Okay, let's go to this problem. It is, I know some of you might have problem with this tension force. So here, again, you have two forces. You need to actually decompose the forces, and but this time you have to calculate the result. So we have one more additional step. You decompose all the forces in the system, and then calculate the resultant of the forces. So we have three forces here. One is 500 Newton on top, 200 Newton going downward to the right, and the tension force. We know the magnitude, which is given in the problem, which is 365 Newton in AC. But we don't know initially the direction or the sign of this force. So if you so is there anyone who have any ideas on how we define the cable forces, how we can solve this problem? Then I would unmute you if you want to talk. Yes, vector addition, but how do you draw the force in the cable? What is the direction of the force in the cable? Of course, let me.
Hey, Siavash, merci.
Go ahead.
Yeah, so basically it's just like the first problem, I believe, guys. So before in the first problem, we had three vectors also drawn, one in the first quadrant, one in the fourth, one in the third. Here it's actually the exact same situation. We have one vector in the first quadrant, one vector in the fourth quadrant, and one vector in the third. Except we don't know the magnitude of the vector in the third quadrant, and that's what we're trying to figure out. So it's kind of like a reverse situation. So what we do is we figure out the components of the two vectors that we are given using the triangles, so the 7, 24, 25, and the 3, 4, 5.
Yeah. Just you're right about the direction.
And then
the direction is
use the dimensions.
Right. You mean the direction of the cable?
Mm-hmm.
The force in the cable is along CA, right?
Mm-hmm. So okay. using the tension.
You are going to calculate the statics. You putting the resultant force equal to 0, right?
Yeah.
But here we don't need to do that here. We are not to that point, or we just need to, because we have the magnitude. If you look at the problem, knowing that the tension in rope AC is 365 Newton, so we know the magnitude. But you're actually right about the direction. So the direction is along AC. Can you okay, so Jimmy said the tension is given in AC. We know it. Okay, thank you. All right, so the tension goes from C to A or A to C.
Are you asking me?
Yes, or anyone else.
I always struggle with this. So the direction of the force is obvious. I mean, the line of the force is obvious. It's along AC, but you have to think, I guess, so it's kind of like you're pulling on C from A. So, and in order for it to just make sense, it would have to point downward, I guess.
At point A.
Yeah, point towards A.
Yeah. What about point C?
Ooh.
Okay, so if you want to stretch the cable, you should initially know that the cable cannot handle compression. So you never compress a cable. It always works in tension. So the force could only act in tension. So when we say tension, we mean pulling. So if I draw the direction, so yeah, and I noticed that the Gavin's answer here and Carlos, and that is perfect. And, so just to uh, clarify, so you have, let me change my, yeah, so if this is your cable and this is the free body diagram of your cable, then you could only pull the cable. So this is the direction of your force on the cable. But here we want to see the force exerted at point C. So if the T here is the force that we are exerting on the cable, so the cable in reaction would exert an opposite force on point C. So if we draw the diagram for point C, because these two forces are acting on point C, then the force that is cable exerting on point C is along C to A. All right, any questions here? Is it clear? All right, so don't worry about it, because we would get to tension problems, cable problems, a lot more. So just let me know if you have trouble understanding this at this point. Okay, so let's make it quick. So now we know the direction. The direction is along AC, and this is that we know the magnitude, and we have all the dimensions. So this would be the free body diagram of point C. So you would get to this free body diagram, I mean, all the time. So the first point of solving statics question is to draw the free body diagram. So in the first problem we already had it. So in the second one I didn't say, but by drawing the forces along BD, we actually drawing a free body diagram. And here again, so you could see on the right that when you translate a physical problem into geometrical or mathematical form, we say it is a free body diagram. And so this is how we calculate the forces. So you know the Cartesian axis, and you must be able to calculate sine and cosine of theta. So oh, you also have the dimensions. So one more point about these dimensions. When you have this triangle under the force, uh, although you do not have the actual distances, because actually the vector is in units of force, so you can't measure the distance. So you show the directions, you show the dimensions by proportions of the components on each axis. So 7 for the first 500, you see this triangle here, 7, 24, 25. These are actually the proportions of this vector. I hope I'm clear enough. Okay, any questions here? Yeah. All right. Okay, I guess we're done. Oh, okay. The last part, the most important part. Okay, so we have to calculate the resultant of the forces. Now that we know the components, we can easily sum all the components in the x direction to get the resultant force in the x direction. And you can do it for the y. So for the x, we get the three components in the x direction. These three are fx that we got in this slide. We sum all of them to get rx, and then we sum all the f of y's to get ry, and so now that we know the components of the resultant force, we can calculate the magnitude by taking the square root. Yeah. Any questions on the resultant force? No problem. So see you all in Wednesday, and just drop me emails if you have any questions until Wednesday. So I would probably re-record this discussion with the annotations, because I didn't have any pen here. So I will record this with all the annotations, and or just probably put the slides with the annotations and put this recorded video on YouTube, and I'll give you the link later. Okay, have fun. All right, this is my email address. Today's evening. I'll post this today's evening on YouTube and send you the URL. Thank you all. Thank you all for coming. I hope this was useful. Okay.